What's up? I'm Vin, and today I want to go through the January 2020 Algebra 2 regions. We're doing parts 2, 3, and 4. But first up here, we have the part 2s, and these are worth 2 credits each. So first up here, we have for n and p greater than 0, we want to know if this expression here is equivalent to this expression. And we have to justify our answer. So that just means we have to show work. Now, the first thing I would do is we're starting off with this, and I would use some of the laws of exponents that we know. So we have p squared times n to the half to the 8th. And then over here we have the radical p to the 5th times n to the 4th. And this is all under the same square root. So first up here, what I would do is use this idea. When you have a power raised to another power like this is equal to a to the b times c. So that's the first rule I'm going to want to use here. That I'm going to do p to the 2nd to the 8th is p to the 16, because we're doing 2 times 8. And then I'm doing n to the 1/2 times 8 is 4. And now another rule that we could use here is that when we have radicals like this with the product on the inside, you could break this up into separate radicals. But what I'm going to write this as, square root of p times square root of p to the 4th times square root of n to the 4th like this. I'm actually going to break it into 3 radicals. And just know if I did p to the 4th times p, that would bring me back to the p to the 5th that's under this radical. And then the square root of n to the 4th is just coming from here. Now, the reason why I'm doing that is because this one here is not going to simplify. Square root of p is going to get left behind to match that last term. But now we could simplify this a little bit more. We have p to the 16 times, we have n to the 4th, and just make that a little neater. So we have n to the 4th, then we have square root of p, and then the square root of p to the 4th is p squared, because p squared times p squared is p to the 4th. And the square root of n to the 4th is n squared like this. So now we're going to use the law of exponents that says when we multiply exponents that have the same base, we add the exponents together. So I have p to the 16 times p to the 2nd. That's going to be equal to p to the 16 plus 2, which is p to the 18. And now I have this one here. I'm going to group these two together, n to the 4th times n squared. And that's going to give us n to the 4 plus 2 is going to give us n to the 6. And then last up here, what I have is just this lone square root of p term like this. And notice this matches what we were trying to show. Is this expression equivalent to this expression? We could say yes. And the justification is all the work that we just showed. Question 26, we want to show why x minus 3 is a factor of m of x, and we need to justify our answers. So with this question here, there's a few ways we could go. But the path of least resistance is to just plug in 3 into the function and see if it equals 0. And the reason being, if m of 3 equals 0, then what we could say is that x minus 3 is a factor. All right, so that's my thought process for a question like this. We could always divide m of x by x minus 3 using polynomial or synthetic division and show it divides evenly, but the easiest way to do this is just to plug in 3. So let's see here. We have m of 3 equals, we have 3 to the 3rd power minus 3 to the 2nd power minus 5 times 3 minus 3. And when we work this out, we could punch this in the calculator, but this arithmetic isn't so bad. So we have 27, that's 3 to the 3rd, minus 9, minus 15, minus 3. And if you work this out, 27 minus 9 is going to give you 18. 18 minus 15 is 3, and 3 minus 3 is definitely 0. So this tells us that this x minus 3 is a factor of m of x. Oh, and just in case you've never seen this notation before, the 3 dots like this in the triangular formation mean therefore. Now, question 27, when I look at this, I just do these questions in my head, but we'll show how to do this with a calculator in a moment. And just know that when you have 2 to the x, and you replace the x with x minus 3, this moves the graph 3 units to the right. Okay, so this is moving us 3 units right. And then when we go from here to 2 to the x minus 3, and then we tack on a plus 4, this sends us 4 units up. So if you know your transformation rules, then this question you could answer just by thinking about which transformations are actually being applied. Now, if we want to verify this here, I would punch in 2 to the x power, and then next I would throw in 2 to the x minus 3. So we have 2 to the x minus 3. We hit the right arrow to get down from the exponent spot, and then we tack on the plus 4. And now when we graph this, I'm going to press zoom 6 just to make sure the calculator's in a nice window setting here. And notice us going 3 units to the right. We're going 1, 2, 3, and then up 1, 2, 3, 4. You see how that would send this graph in blue directly on top of this graph in red. So our answer is looking good. Question 28, we have this parabola and we have a focus of 3, 1, and we need to determine and state the equation of the directrix, and the use of the grid is optional, but we are definitely using that grid. So me personally, when I do questions like this, I like to use the grid because the concept of a parabola is very visual. I have trouble memorizing all the formulas, especially the formulas for the focus and directrix, but I know what a parabola is and I know how to draw this stuff out. So what we have here is the focus is at 3, 1. So I'm going to go over 1, 2, 3. And I'm going up 1 unit, and that's the location of our focus. But next, what I could do is I could use this idea that in general you have y equals a times x minus h squared plus k. This is the vertex form of a quadratic, and notice that our parabola y equals this quadratic equation is in vertex form. So here we could see that the vertex of this, the vertex is going to be located at the point 3, 6. And notice because we have x minus h, this represents our h and our k value of our vertex. So the h value is always opposite. So x minus 3, our x coordinate of our vertex is going to be positive 3. And then k is going to be equal to 6. So now I go over to the graph and we're up 1, 2, 3, 4, 5, 6. So that brings us over here. And this is the location of our vertex. But now since this is a negative parabola, notice that the coefficient is negative 1 over 20. This thing is going to open outwards like this, or I should say opening downwards like this. It's going to be a frowning parabola if I were to draw the whole thing. So now the concept of a focus and a directrix. Just know that when you have parabolas, there's 2 different kinds you could be looking at. And you have a directrix and you have a focus like this, and then the parabola opens upward. And remember, any point on the parabola is the same distance from the focus as it is from the directrix. So you could have something like this. Or you could have a situation like this where you have a sad or a negative parabola like this, where you have the focus, you have the vertex, and in this case, the directrix is above, like this. So any point on your parabola is the same distance from the focus as it is from the directrix. And I'll just label both of these as the horizontal line, in this case, is our directrix. So notice this is a situation where we're in the second case here, where we have the focus, the vertex, and the directrix is going to be above since this thing is opening out this way. And now I just have to count the distance. So remember, our y value for the vertex was 6, so that's a distance of 5. And I can even count it. I go up 1, 2, 3, 4, 5 like this. So my directrix would be 5 units up. I would go up 1, 2, 3, 4, 5 to this location here. But my directrix in this case is going to be a horizontal line like this. So now to write the equation of the directrix, we just have to know where does this thing hit the y-axis, and we're going up 1, 2, 3, 4, 5 from 6. So that's going to send us up to a height of 11. So that line, the equation of this line here is going to be y equals 11. This is the equation for our directrix. Question 29, we have a geometric series, and we want to write a geometric series formula S sub n for the sum of the first n terms. Then we're going to use this formula to find the sum of the first 10 terms. Now, this formula is in the back of the test. If you look to the reference sheet in the back, S sub n is equal to A1 minus, we have A1 times r to the n over, and then we have 1 minus r. And just know A1 is your first term. So the first term here is 300. And then r is the ratio, the common ratio that we multiply by to get from one term to the next. And just know, the trick for finding the common ratio of a geometric series is to divide any 2 consecutive terms. So I take 360 and I divide by the one right before it, 300. And if I simplify this, divide the top and bottom by 60, we're going to get 6 over 5, which equals 1.2. So here's our common ratio. And if we wanted to check this in the calculator, you could just multiply by 1.2, and you're going to get from this term to the next term, and so on. So now what we could do is, first we could write our formula. We have S sub n equals, A1 is 300, so we have 300 minus, A sub 1 again is 300. R we found here to be 1.2, so we have 1.2 to the n power divided by, and we have 1 minus r is 1.2 like this. So they didn't tell us to simplify the formula, so we could stop here, but if that bothers you, what you could do is you could call this, we have 300 minus 300 times 1.2 to the n power, and if you were to do 1 minus 1.2, that would be negative 0.2 like this. So either one of these is fine, but we're going to use one of those formula to find the sum of the first 10 terms. So just know we're going to be finding here S sub 10. We're going to be plugging in n equals 10 to our formula. So we have S sub 10 equals, and now we have 300 minus 300 times we have 1.2 to the 10th power, and we're dividing by negative 0.2. Now, just to make sure you're accurate, what you could do is press alpha y equals enter to pull up a blank fraction like this. And we're going to have 300, and we're subtracting 300 times, and we have in parentheses 1.2 to the 10th power like this. And now in the denominator, we had negative 0.2 like this. And we're rounding to the nearest 10th, so this is going to be 7787.6. So we have 7787.6. This is the sum of the first 10 terms. Question 30, we have 3 light waves. We want to know which one has the longest period. So thinking about this, there's a few ways you could find the period of a wave. And one of the ways is you have a wave like this. You could measure the horizontal distance from one high point to the next high point. Or what you could do is, and let's say I make this wave a little bit nicer, so something like this. The other way would be to measure the horizontal distance from one of the low points to the next low point. But then the third way, which makes the most sense for this question, is to double the horizontal distance from one high point to one low point, since these waves are all symmetric. Now, let's start off with A. We want the period of A. And the way I do this is I look for significant points. A is in light gray, so the high point is over here. So I'm just going to label this A, and that's occurring right between 40 and 60. This is happening at 60. And I'm just going to write that there because these are sometimes hard to remember, so I like to write it in. And then the low point is going to occur at 340 nanometers. So at wave A, the low point happens at 340. So if I want to find the period of A, what I'm going to do is I'm going to double the distance from the high to the low. And the distance from the high to the low in this case is 340 minus 60. And this is all in nanometers. So we have nanometers like this. And this is equal to, that's going to give us 280 times 2 is 560 nanometers. Now, just know, what we have here is we just have to justify our answer. So this is our justification with that we're showing some work. Now, the period of wave B, and that's the one that's dotted, we could look for a high and a low point like this. So notice the high point is over here. And that's occurring at about 180. Okay, so this is at 180. So this is for B. And this is occurring at 180, and then the low point occurs right at 400. Okay, so for B, the low point is at 400. And I'm going to do double the distance from 400 to 180. So now I measure that horizontal distance it takes to complete the wave. And once again, I'm doubling it because if I go from a high to a low, that's just half of the wave. And we're in nanometers still. So this now, let's just do the arithmetic here. This you could just punch in a calculator, but 400 minus 180 is going to give us 220, times 2 is going to give us 440, and we have nanometers. And for the last one here, the period of C, I'm just going to identify this on the graph also. And notice C goes down here. It starts at a low point at, this looks like 60, so this is for C. Our low point is at 60. And then our high point happens up here at, let's see, that's going to line up with 380. Okay, so yeah, they're pretty precise with these. I mean, here, when you justify, you could just say that it takes more than the entire graph for this graph of wave C to complete a full cycle. Like, that's enough to say that C is going to have the longest period, but I just want to be a little bit more precise here. So we have 2 times, and now we have 380 minus 60 nanometers like this. So that's going to give us 280 times 2, and I'm sorry, if we work this out, 380 minus 60 is 320. 320 times 2 is 640. So you have 640 nanometers. So now we could just answer this. Wave C has the longest period. Question 31, I like this quote by Abraham Lincoln. You give me 6 hours to chop down a tree, I'm going to spend 4 hours sharpening the axe. And that's what that means for a question like this. You just have to really think carefully about what you're about to write, because all you have to do is write the equation, but you have to write it correctly. So we have biologists, and they're looking at bacteria. There's 100 to start, and then every 30 hours, the amount of bacteria is going to double. So it's going to go 200, then 400, and so on like this. And we need to write an equation, or we could say a function here, b of t, where t represents hours and b represents the number of bacteria. T hours since the experiment began. So we're starting with 100 here, and we're multiplying by 2 repeatedly. But the factor that we have to consider here is that it's doubling every 30 hours. So we can't just say to the t power like this, because in 1 hour, that means we're going to double. So we need to do t divided by 30, because think about it. If 30 hours goes by, we have 30 divided by 30 is 1, and we're multiplying 100 by 2 to get the next amount of bacteria, which is 200. And then 60 hours, it would double twice. So we'd have 60 divided by 30 is 2, and then we'd be multiplying 100 by 2 twice to get to 400. So this is looking like the function here, but since that was just in our thoughts, let's actually write it on the paper here like this. And our function is going to be b of t equals 100 times 2 to the t over 30. Question 32, we just have to graph here. So I'm going to clear out what we had from before, and we're going to type this function in. We have x to the third power, so I hit x, and I hit this up arrow here, or I think they call it the caret button. And we have minus 4x squared plus 2x, and then plus 7. So for this one, I'm just going to press zoom 6 just to make sure the graph is in standard form like this. And what we need to know, we're going to press second graph like this. And I'm going to zoom out a little bit to about this section here because our graph is going to run out of space. We're not going to be able to go down to negative 21 or up to 15. So these points make the most sense to plot. So I personally like to write out a table. So we're going to have x, y, and I like to do the table just in case your art is not that amazing. Then the table will kind of back you up here so that they know what you were going for. So you have 0, 7, 1, 6, and then you have 2, 3, and you have 3, 4. So for this one, now we just plot these points. So this is negative 1, 0. Then we have 0, 7. So I got to count to 7. 1, 2, 3, 4, 5, 6, 7. Okay, so we're going up here. And then we have 1, 6. So we're just going to go over here, but we're going to go down 1 from where we were before. And then we've got 2, 3. So going up 1, 2, 3. And then we've got 3, 4. So that's going to bring us to this location. All right, so these are just some of the significant points that we have. But now, the reason I like to look at the picture too, so that you don't just draw this in like a crazy way. Make sure that you're trying to draw this to match what the actual function looks like. This is a cubic function, so it's going to go up, down, and up. So here, just very carefully, I'm going to connect this. Now you see I kind of missed a little bit, so I'll try that one more time. So here, just at the regions, take your time. So then over here, for the next part, we're dropping down. And then we start to turn. Let's try that one more time like this. So we're going down and then we're going back up. Okay, so this is a graph of our function and this would get us the full credit. I would include the table, plot the points, and connect them to the best of your artistic ability. So question 33, we have Sonia is cutting wire to construct a mobile and she cuts 100 inches for the first piece, then 80 inches, and then 64 inches for the third piece. And assuming this pattern continues, we're going to write an explicit formula for A sub n, the length in inches of the nth piece. So for this question here, what you should be thinking about is how is this sequence of numbers changing? So we're going from 100 to 80 to 64. So your first instinct might be to see if this is an arithmetic sequence. And notice we're going down 20, but then we're going down 16 to get from 80 to 64. So this tells us that this is not arithmetic, that this is geometric. Okay, this is going to be a geometric sequence. So here we have to figure out what is our common ratio. And the common ratio we could find by dividing one term, let's say in this case 80, by the term before it, which would be 100. And now this would simplify to 4/5 or 0.8. So now you got to think about how do you get from one term to the next? Well, to get from one term to the next, you're going to multiply by 0.8. So then the next thing you might think about here is that the first number in the sequence is 100. But then 80 is the same thing as 100 times 0.8. And then if I want to get to the next term, 64, I would multiply by 0.8 again, or I would multiply by 0.8 squared. Okay, so this is the pattern that should be going on in your head, that we're multiplying by 0.8 each time. But one thing to be mindful of is that this is the first term. So this is our first term, this is our second term, and this is our third term. So we need to come up with the pattern here, A sub n. So A sub n is going to be equal to, we have 100, that's our first term, times 0.8, but think about it very carefully. For the first term, it's basically 0.8 to the 0. For our second term, it's 0.8 to the first power. And then for the third term, it's 0.8 to the second power. So the power is 1 less than the number of terms. So here we would just tack on an n minus 1 like this. So this is going to be our A sub n formula. We have 100 times 0.8 to the n minus 1. So for the second part of this question, we have Sonia has 40 feet of wire and she wants to cut 20 pieces total. And we want to know, does she have enough wire? We need to justify our answer. So for this, what we should find first is how many inches are there in 40 feet? Because notice we have 100 inches, 80 inches, 64 inches. So the sequence was in terms of inches. So let's convert. So we have times 12 inches over 1 foot. And now feet over feet cancel, giving you 480 inches. So from here, what you're going to do is you're going to find out how many inches total if we add up all 20. But notice this is geometric. The pattern that we should note here is that this is a geometric sequence here. So to add them up, we're going to use the formula. So the formula we should be thinking of next is the sum of the first n terms of a geometric sequence is equal to the first term times, and then we have 1 minus the r value to the n power divided by 1 minus r. Okay, now this formula is given to you on the reference sheet, but this is the one we want to use. But in this case, we're going to look at what happens when n equals 20. So here, we're going to have the sum of the first 20 terms. So first, we're going to have our first term. This is our a1 term here. We're going to have 100 times 1 minus the r value was 0.8. And n equals 20, so we're going to raise this to the 20th power. And then we're dividing by 1 minus r, so 1 minus 0.8. So now we can just type this in. We're going to press alpha y equals enter to pull up a fraction, and we have 100 parentheses, and then we have 1 minus 0.8 we are raising to the 20th power. And then we're going to divide by, let's just hit the right arrow to get out of the exponent spot, but we're dividing by 1 minus 0.8. And now here, this is going to work out to, so we have 494, and let's round to the nearest thousandth place. We have 235 inches. So now just think about it. If Sonia has 480 inches of wire and she needs this much, she doesn't have enough because 494.235 is greater than 480. Question 34, we have to graph, then we have to state the domain of the function, and then we have to state the equation of the asymptote. So let's get going here. So we'll type this in. We're going to the y equals. Let's clear out what we had before, and we're going to press math. We're going up to letter A here for log base, and this allows us to type in custom log. So we have a base of 3, and then inside the log here we have 2 minus x. So we do this, and just to make sure the graph is nice, I'm going to press zoom 6, and that puts it back to normal. So now let's take a look at the table. We press second graph, and if we scroll up here, notice that we have a bunch of errors here, but then once we get to x equals 1 and all values less, then we actually get significant values here for our y column. But let's go ahead and take a screenshot of the table for these select values. Now I'm just going to leave the graph here in the corner so we have something to refer to, but if I was making a table of values here, what I would include in my table is just the whole number coordinates. So negative 7, 2 is a good value here because that we could actually graph, and then we'll have negative 1, 1. And we'll have the point 1, 0. So there's really just 3 significant points we could graph here. So we have x equals 1, y equals 0, then we have negative 1, 1, which would put us here. And then we have negative 7, so we're going 1, 2, 3, 4, 5, 6, 7, and up 2. So I'm just going to go ahead and label this. So this is negative 7, this is negative 1. We have 0, 1 like this. But now, one of the ideas to find the asymptote, the vertical asymptote, which we're going to have to know later. Notice the calculator is only so perfect, but we could visualize our asymptote is going to be at x equals 2. And the way I recognize it is that when we have a linear term on the inside of a log function, when x is equal to 0, that's your vertical asymptote. So notice that x equals 2, we're going to have a vertical asymptote like this. Okay, so that means when we sketch our graph that we want to be approaching this dotted line here. Okay, so that's what we're aiming for, is this dotted line. So now I'm going to go ahead and connect the points here. So this is going kind of like this, and I'll make it as neat as possible. So let me try that one more time. So we'll do actually a third time. All right, so something like this, all right? Not the best drawing in the world. I really want to just redeem myself here. I could do way better than that. All right, that's definitely way better. But the way that I know to draw these is I think about what an exponential function looks like. So the exponential function looks like this. So a log function is just the opposite of an exponential function. So it has symmetry over the line y equals x. That's what it means for two functions. So if this is f and this is f inverse, they have symmetry over y equals x. So when I'm drawing a log function, I just think of doing the opposite of an exponential function. So this is our function here for f of x. But now that we have this graphed here, we can just think the domain of this function is going to be all values x that are less than 2. Because notice when x is equal to 2, what we have is we have a 0 inside of our log, and that's no good. So for all x values less than 2, the graph does exist here. So our domain is x less than 2. And the equation of the asymptote, this is the line x equals 2. Okay, just be careful here. This is a vertical line. So x equals a constant is your form for vertical lines. If you wanted a horizontal line, just know, like if it was, I'm just thinking about this, I wouldn't write this actually on the test, but if you had a line y equals 2, just be mindful that this would be the horizontal line going like this. Okay, but x equals 2 is our vertical asymptote. Question 35, we're going to algebraically solve the system of equations. So here, what I would do is I would solve this second equation here for x or y, and then substitute it into the first equation. So here we could start by doing plus 1 on both sides. And we've got x plus y equals 1. And now it doesn't matter which one we solve for, but let's say we solve for y. So I would do minus x on both sides. And now we have y equals 1 minus x. And now here we're going to plug this into the first equation. So what we're going to have is we're going to have x minus 2 squared plus, but notice here, instead of y minus 3, y is equal to 1 minus x. And then I'll tack on the minus 3. And then we throw in our square equals 16. So notice I just replaced y with 1 minus x. And now we just simplify a little bit. This is going to be x minus 2 times x minus 2. And now this one here on the inside, we're going to have 1 minus 3 is negative 2. So we're going to have negative x, and then we're going to have 1 minus 3 is negative 2. And this is being squared like this, and this is equal to 16. Now, this might throw some people off having the double negative here. So what we could do here is just know that when you square this, a lot of stuff is going to turn positive. So just be careful with the negatives. So here, we're going to have x minus 2. So let's just make sure we distribute this neatly. We have x times x, because we're multiplying x minus 2 by x minus 2 is x squared. And then we have minus 2x. Distribute here, we have minus 2x. And then we distribute negative 2 times negative 2 is positive 4. And now for this part, I'll rewrite this in red. This is going to be negative x minus 2 times negative x minus 2. And this is all equal to 16. So in the next line, we could just combine this stuff here. We have x squared minus 4x plus 4. And now we're going to distribute here. We have negative x times negative x is x squared. Then we've got negative x, and let's draw that neater. Negative x times negative 2 is positive 2x. And then we get another positive 2x. And then we get another, well, we get a positive 4 at the end here. So everything turns out positive because we just did all negative times negative. And this is still equal to 16. So now let's just combine all the like terms on the left. We have x squared plus x squared. That's going to give us, don't say x to the fourth. That's going to give you 2x to the second. And now what we have next, we have 2x plus 2x. That's going to make 4x. And then 4x minus 4x is going to cancel. So these three terms are going to cancel each other out. And then we got 4 plus 4 is going to give us 8. And this is equal to 16. So now from here, what we're going to do is subtract 16 on both sides. And now we've got 2x squared minus 8 is equal to 0. So from here, I would factor out a 2, and we'd have x squared minus 4 is equal to 0. And notice this factors very nicely. This is going to give us, well, first we'll just tack on the 2, and then we have x plus 2 times x minus 2 is equal to 0. So now just know we could set each factor equal to 0, but I never set the constant equal to 0 because that's just false. 2 is never equal to 0. So if you set this one here, x plus 2 equals 0, that's true when x equals negative 2. And then x minus 2 is equal to 0 when x is equal to 2. So now let's get our solutions. We have x equals negative 2, and now I could plug into that y equals 1 minus x that we created. So when x equals negative 2, y is equal to 1 minus negative 2. And that's just going to be equal to 3. So I'll write our solutions over here. So our solutions, we're going to have the first one is negative 2, 3. So we have this, and I'll find our second solution now. We have, remember, x equals plus or minus 2. So when x equals positive 2, y is equal to 1 minus 2, which is negative 1. So now this gives us our second solution, the point 2, negative 1. But here is our solutions to the system of equations. Question 36, we have air pressure at selected altitudes above sea level, and we need to write an exponential regression equation that models these data, and we're rounding everything to the nearest thousandth. So let's type in this data. We're going to go to stat, and we're going to go over here to edit, and now we just fill in the table. Now, once we have the data inputted here, we're going to press stat. We're going to go to the right to calculate, and we're calculating an exponential regression. So notice here, we just got to scan, and let's see, where is exponential regression is down here at 0. So we press enter and just keep pressing enter, and now calculate. And these are our significant values. So now we'll just write out our equation. We have y equals, and notice our coefficient a, we could just round to the nearest thousandth place. It's going to be 101.523. So we have 101.523. And now we have our term b here, that's our base of our exponential, to the nearest thousandth is going to be 0.883. So we have 0.883, and now we just tack on our variable here. This is raised to the x power. Now to finish out this question here, we're going to use algebra here to determine the altitude to the nearest hundredth this time of a kilometer when the air pressure is 29 kPa. Now one thing to point out here, the 29 is coming from the y column here. Notice that the air pressure, the units here, match what we're trying to find. When is the air pressure 29 kPa? So now we can set up our equation. We're going to have 29 equals, and we have 101.523, and then we have times 0.883 to the x power. But now what we're going to do here is we're going to start by dividing both sides by 101.523. And I'm going to leave this in fraction form until the very, very end when we get the actual value. So we divided the right side by 101.523, so we're going to repeat this on the left. And now what we have is, and I'll leave a little space, we're going to have 29 over 101.523 is equal to, and I'm going to leave space, we're going to have 0.883 to the x power like this. So now to get the x to come down, we're going to use natural log. Now I could use any log I want. I could use log base 10 or log base anything, but I'm using a log on both sides because what that's going to do is going to allow us to bring this x to the front of the log. This is one of our properties of logs here, but this x could move to the front of the log expression on the right. So then in our next line, what we're going to have is we're going to have natural log of 29 divided by 101.523 equals, and we're going to have x times natural log of 0.883. So now the last bit of algebra to do is divide both sides by natural log of 0.883. So we're just going to divide here. We have 0. We're dividing by natural log of 0.883, and we're going to do the same thing on this side. And now the rest is just calculator work. So we go back to the main screen here, and I'm going to press alpha y equals enter. And now we've got natural log of 29 divided by, we have 101.523. And now we'll close the parentheses, and on bottom we're going to write natural log of 0.883. And this tells us our answer to the nearest hundredths place is going to be 10.07. So after this all cancels out here, we have x equals 10.07 kilometers. Okay, so we made it to part 4, the final boss, and this question is worth 6 credits. So question 37, Sarah is on drugs. No, her doctor is prescribing her drugs for her sinus infection. And the doctor prescribes nasal spray and an antibiotic. The nasal spray is N of T, and the antibiotic is A of T. So at least there's alliteration that makes it easy to remember when the first letters match. And here, first we have to determine which drug is made with a greater initial amount of active ingredient. Justify your answer. So in math, when you hear initial, that means t equals 0. So here I would find n of 0 and I would find a of 0. And the second one is much easier to find. 9 over 0 plus 3. Just know, 9 divided by 3 is 3. So this, we could say here, 3 milligrams. Oh, just know, general rule of thumb is for the Regents, you want to double check the rubrics, but they do not take off points if you leave out units. So here, they're not saying indicate units of measure. So you could just write 3, but I personally like to write the units in. So here, n of 0, we could find that by substituting 0 plus 1 over 0 plus 5. And then we have plus 18 divided by, plug in 0, you'll get 0 plus 15 is this. And then this we could simplify just adding the fractions ourselves. But we could also just use a calculator for this. So ultimately, you would just have 1 over 5. And I don't have to use alpha y equals enter here like I did before, because these fractions are just kind of simple. So I have this plus this, and then I could leave it as a decimal. Or here, what I could say here is I could press math enter, enter, and I could write this in as a fraction. But either of these are going to be fine. So as a decimal, this answer simplifies to 1.4 milligrams. So just looking at it, the antibiotic is going to have a greater initial amount of active ingredient. For the last part of this question, Sarah's doctor tells her to take both drugs at the same time. We need to determine algebraically the number of hours it's going to take for both meds to have the same amount of active ingredient in Sarah's bloodstream. So here, this is really just saying when is n of t equal to a of t? And if we copy down the original functions from before, we have t plus 1 over t plus 5, plus we have 18 over t squared plus 8t plus 15 equals, and now the function for a of t was 9 over t plus 3. Now with these questions, what I like to look for first is the values of t that are not allowed. So here, -5 would be bad, because that would make this fraction have a 0 denominator. And then -3 would also be bad. Now the reason I like to do this ahead of time is that if any of these answers show up, we immediately reject them. So that's a common trap that they like to set, is with rational equations, like they try to make you forget to reject one of the forbidden values. So here what I would do first is, we'll rewrite this. We have t plus 1 over t plus 5. I'm going to leave a space, plus 18 over, we have t plus 5 times t plus 3. So I could factor this second one pretty nicely here like this, equals 9 over t plus 3. So the next concept that you need for a question like this, so you need to look out for the undefined values, but you also have to look out for the least common denominator. So here, our least common denominator is actually going to be t plus 5 times t plus 3. And I needed a better thought bubble for that, but you get the idea. So here, what I would do is I would multiply the first and second fractions to make them have a matching denominator with this middle fraction here. So the first fraction we would need to multiply by t plus 3 over t plus 3. And now the last fraction we would need to multiply by t plus 5 over t plus 5, because notice now all the denominators match. And now algebraically, what we are allowed to do, since we already mentioned which values of t are not allowed, now we could go ahead and safely cross out all three denominators like this. And now what we have left is these terms across the top in the numerator spot. So I would do first t times t is t squared. Then we have t times 3 is 3t. Plus 1 times t is t. Plus 1 times 3 is 3. And now we have plus 18 equals, and now we're going to have 9 times t plus 9 times 5 is 45. So now just algebra, we have t squared plus 4t plus 3 plus 18 is going to give us 21 equals 9t plus 45. Now, for this, I would just do 2 steps of algebra in one. Subtract 9t, and then in the same breath, subtract 45. So now these cancel on the right, leaving us with 0, and we have t squared. 4t minus 9t is minus 5t, plus we have 21 minus 45 is negative 24. So now factor again. This is going to factor nicely to t minus 8 times t plus 3. And I already see one of our traps set for us. This will give us a root of t equals negative 3, which we already said is forbidden. So this factor is going to give us a root that we're going to reject. So this one here, once again, t equals negative 3. This one we could reject. Okay, we're going to cross this one out. But the second factor here, t minus 8 equals 0, occurs when t equals 8. And this gives us our solution to the second part here.